Well, good afternoon, everyone. Thank you very much for joining us today for the first installment of the Fall 2011 Pavinar series. Today's topic will talk about the differences between Portland cement concrete and asphalt concrete. And as Andy pointed out, I have taken away microphone privileges for the participants just because sometimes they're left on and there's background noises. So if you have any sort of problems with that, or if you wanted to contact me, please use the chat function. So David made a very nice segue into the logistics of Pavinars. If you can't hear me talking right now, I encourage you to check your volume and or speakers. Could I ask either Tim or Andy, are you able to hear me? Or Bob? Just write a little note in the chat box. Okay, thank you very much. So that means that the audio on this end is functional. So David, I'm not exactly sure what the problem is on your end, but I apologize. My specialty is not in computers and or volume control. So maybe if you could scooch down to Bob's office if you guys are in the same area, or you can fool around with the volume controls on your computer. That would probably be the best way to go. Also, in addition, I will pause periodically during the Pavinar and ask if there are any questions. And I would ask you to use the chat box on the left side of the screen, which you've all found. The reason I ask to do that is because sometimes if a chat pops up, I'll automatically glance over there and it may break the concentration. So I would recommend waiting until I ask for questions and then we can all have a discussion together. I think that would be a good way to go. And then finally, professional development hours. I've had some questions about those, and I was able to go through the university and find out that I'm able to grant them. So after this is over, I will email you all the professional development hours completion certificate using the emails that you inputted when logging on, and I will be able to, and you'll just fill your name in and you'll receive one professional development hour for this session. So for this first Pavinar of the Fall 2011 series, we're going to start with a very broad overview of the differences between Portland cement concrete and asphalt concrete. Both of these are obviously types of pavements, but how are they different? And what we'll do is we'll focus on more traditional definitions. I realize that there are a lot of innovative materials out there, innovative techniques, and this presentation is an extremely broad overview that just kind of goes over the fundamentals. Now, if you're interested in a specific area, I recommend that you email me or go to the website and send me a suggestion about a topic you're specifically interested in, and we'll certainly consider those. So the outline of today's presentation is we'll have a brief background talking about important terms and the purposes of pavements in general. Then we'll talk a little bit about material properties. What are the components of pavements and what types of pavements, both Portland cement concrete and asphalt concrete, are out there. We'll cover mix designs, both the materials and some mechanisms behind the mix design process and what happens within the materials. And then finally, an overview of both the construction and the stresses and maintenance in the field. So we're going all the way from a background into laboratory and then into the field. And again, I just wanted to remind you that this is a very broad overview. So again, if you want more details, I encourage you to put that in the suggestion box. So there are many different terms used in the pavement industry when we talk about Portland cement concrete and asphalt concrete. Portland cement concrete is often called rigid pavement, PCC, white top or cement, and there's probably more names out there. Asphalt concrete, flexible pavement, hot mix asphalt, or HMA. Now of course we have warm mix asphalt as well. That is an example of one of the innovative technologies that we won't be covering today. AC, blacktop asphalt, and bitumen. These are all terms out there, so if you're either reading trade magazines, journal articles, you'll see a lot of these different terms. But for the sake of this presentation, we will use PCC for Portland cement concrete and AC for asphalt concrete. So what is a pavement's purpose? Well, regardless of if it's a PCC pavement or an AC pavement, pavements must provide some basic functions. You must have a safe traveling surface, structural capacity for the loads apply, and in my field I tend to focus on highways, but pavements are used everywhere. They're used in airports, seaports, so we want to realize that this is kind of a broad overview of pavement materials, but once you start going in specific areas, whether it's a surface street in a town that sees a lot of cars, or an interstate that crosses the country that sees more trucks, airports see airplanes, there's a lot of different loads that you need to account for. You also want to make sure that the pavement is smooth and is able to drain water. Water pooling is a very significant problem that can cause hydroplaning and increase accidents. And finally, you want enough surface friction to prevent vehicle slippage. We could theoretically make a pavement out of steel, however, it would do the first four but not be able to do the last one. It would become very slick under wet weather conditions. And although Arkansas has not seen a whole lot of rain lately, that's somewhat unusual. So you want to have surface friction in order to prevent the vehicle slippage. And again, regardless of if it's Portland cement concrete, PCC, or asphalt concrete, AC, you want to make sure that the pavements are able to provide these functions. So what is a pavement structure? When a person is driving along a roadway, they actually just see the very top level of the pavement, which is the surface area. But there is a pavement structure underneath this surface layer. And you can see here in the schematic, the surface layer is generally 6 to 12 inches thick, and it can be either PCC or AC. Typically, for PCC pavements, you have one lift, a single pass in order to lay that surface layer. Whereas for AC, you often have multiple lifts, and that's because you need to compact that AC layer, and in order to get good homogeneous density, it needs to be approximately 2 to 4 inches thick. And you want to also have a base course for some pavements or a sub-base course. I'll go into more details about the different types of base courses and sub-base courses you have between a PCC and an AC pavement. And of course, these pavement structures all sit on top of the natural subgrade. And the natural subgrade is what is actually sitting in place before you even start building the pavement. And the thickness and material design for each of these layers depends on many, many factors. The application that you're putting in, again, is this a highway? Is it a county road? Is it a surface street? Or is it an airport? Something that sees very different loads. And that goes into, you need to account for the loads that are applied on there. Residential street usually sees cars, maybe one truck or two every once in a while, versus an interstate sees a lot of heavily loaded 18-wheelers. And then of course airports see planes, anywhere from small turboprops to jumbo jets. You also need to worry about the local materials, what's available in your area. A lot of areas have better aggregates than other areas, so you need to take into account what is the cost of the aggregates in your area. It might be less expensive to ship it in from a different area, but that could play with your cost structure. Also, you need to think of the pavement history. There's a lot of the original interstate system was built with Portland cement concrete, and that has since deteriorated slightly, so some states are going with asphalt concrete overlays. So that's a different type of pavement structure, not one of those traditional types, but it is something that needs to be taken into account. And finally, the environment. Obviously, there's warmer and cooler environments across the country, across the state of Arkansas even, and also the amount of moisture and other factors, the amount of rain and amount of freezing that you have. So these are all factors that go into determining what the pavement structure is. And as I mentioned before, we're going to be focusing on the surface layers of a pavement structure. This is where the PCC and the ACC are placed. And both PCC and AC have some sort of rock, which we call aggregate in the industry, and a binding agent. Traditionally, PCC uses Portland cement, hence the name Portland cement concrete, as its binding agent, and AC uses asphalt binder or asphalt cement to bind it together. And while the mechanisms of how the binding agent works are quite different, we will cover that later, but the point is that you have some sort of rock that's held together by the binding agent, and that's what provides the strength you need in your surface layer, and also that's what provides the safe traveling surface, the smoothness, the drainage of water, and the surface friction. So when you're thinking about the different types of PCC pavement, there are 4 general types. Some are more common than others, but it really comes down to reinforcing steel and contraction joints. So for example, jointed plain concrete pavement, or JPCP, does not have any reinforcement steel, but it does have contraction joints to control cracking. Whereas JRCP, jointed reinforced concrete pavement, has both contraction joints and reinforced steel to control cracking. A third type is continuously reinforced concrete pavement, or CRCP, which does not have contraction joints, and the cracking is held together by continuous reinforcing steel. So here you have the 3 options of steel or no steel, and contraction joints or non-contraction joints. And pre-stressed concrete pavement, or PCP, is not as common. It's sometimes used in airports. You also sometimes see it on bridge decks now. If it's cast in other places, it may be pre-stressed. But really those top 3, the JPCP, the JRCP, and the CRCP, are the 3 biggest ones. And in general, again, of course, it depends on the application, but you have 6 to 12 inches of PCC on that surface layer, and then you can have 4 to 12 inches of base or sub-base, which is optional. And that would depend on what kind of loads you're expecting and the quality of the material that's already in place. Underneath that, you can have either the natural subgrade or some sort of, for example, lime stabilized subgrade. There's a bunch of different things you can do with the subgrade as well. Here's a little schematic of the different types of PCC. In the upper left-hand corner, picture A is a picture of the JPCP, the jointed plain concrete pavement. You can see they have the transverse joints in place, and those can have dowels or they might not have dowels, but there is no reinforcing steel. Or to the right, in picture B, the jointed reinforced concrete pavement, you do have that wire fabric in there, that continuous reinforcement that gives it its name. You also have the transverse joints, and you can have those with or without dowels. The third option, number C, the continuous reinforced concrete pavement, you can see has no transverse joints but does have that continuous reinforcement. And then the PCP, the pre-stressed concrete pavement, has wire strands in it in order to give it that pre-stressed ability. Switching gears now to asphalt concrete, or AC pavements. There are a couple of different types of AC pavements. One is a conventional AC pavement, and you can see a big difference right here. We're still talking just about the surface layer, but you'll see there's many different layers within that surface layer for an AC pavement. You generally have some sort of seal coat on the very top, and underneath that a surface coat, followed by a tack coat and a binder course, and then a prime coat on the bottom. So when you're thinking about how an AC pavement needs to be constructed, those thinner layers, you're probably going to have multiple lifts as you go down into that pavement structure. You also have some granular unbound material below the bituminous material, and those can be base courses or sub-base courses. And then you have the subgrade at the bottom, which is the natural material, and it's often compacted before any pavement or anything is built on top of it. Now, in addition to the conventional AC pavement, we also have what's called full depth AC pavement. And here you have bituminous layers, including your seal coat, a surface course, tack coat, and then you just have a base course with generally no granular unbound layers beneath that. So it's a much thicker depth of asphalt concrete with no granular materials. But you still have that subgrade material underneath the entire pavement structure, which can be either prepared or natural. One thing to remember also about AC pavements is because you have all of these layers, you generally have higher quality material along the top on those surface layers, and then as you go down, the material quality goes down a little bit. Now that's not to say that what's underneath is not adequate for its needs, but you don't need that smooth riding surface on the top, which generally has a little bit more asphalt cement in it. So you can have slightly larger rocks, slightly less asphalt cement in those lower materials, so it may not be as strong, but it does provide the structure that's necessary for the pavement. Here are some schematics of the types of AC pavements, and you can see these different layers in the conventional pavement. You have your surface course and your binder course and your base course. All of those are bituminous materials. That base course can also be a granular material, but between those you have your seal coats, your tack coats, and your prime coats. When you lay down two bituminous layers, one on top of another, you need to have some sort of coat in between them so they can bind together. Unless you construct one very, very quickly after another, you may have delamination where the surface course can literally lift off of the binder course if you're not careful and if you don't have that seal or tack coat. Whereas if you look at the full depth pavement, you have your asphalt surface. There's probably a tack coat under there. It's not indicated in the drawing, but they should have a tack coat. And then beneath that, you simply have an asphalt base. So instead of having the binder course, the base course, and the sub-base course that you see in the conventional pavement, you simply have an asphalt base. And beneath that is the prepared subgrade. And there are some depths along the right-hand side there as well to give you an idea of how thick these different pavement layers need to be. And of course there's many variables when determining how thick they are, and that could be a topic of a whole nother Pavinar. So in summary, the different types of pavement with PCC and AC. For PCC, usually you have one lift of the surface course, and it can be placed either on the subgrade or on a base course. You sometimes have reinforced steel. You sometimes have contraction joints, but that goes back to the different types of PCC pavement, whether or not you have that reinforcement and whether or not you have those contraction joints. Whereas with AC, you usually have multiple lifts so you can achieve your density. Those lifts are anywhere between 1 to 4 inches thick in general, and that allows you to have an even density throughout the entire depth of the pavement. You do need tack coats in order to bond those different lifts together. If you don't supply that bond, you could have the delamination where the layers come off of each other. And then finally, you need to have a base course between the surface layer and the subgrade. And that prevents any of the material in the subgrade from moving up through the pavement structure, whether it be in a crack or if there's an area that's segregated with very high voids. Material can move up through the pavement structure and get to the surface, which is something you do not want. So this is the first part of the presentation, talking about the pavement summaries, the different types of pavement, and a little bit about the material components. So I'm going to pause here for a bit, and if you have any questions, please feel free to type them in the chat box on the left side of the screen. Okay, no questions yet. I'll take Andy's answer as everyone's. Again, if you do have any questions, maybe I can suggest you just type in "I have a question" and hit enter, and then you can take some time to formulate a question. I know sometimes when I start trying to type long sentences very quickly, I get bogged down in the spelling, and since this isn't Microsoft Word, we can't just right-click and correct spellings. But if you do have any questions, please let me know. So transitioning into mixed design practices. Now, As we go through these 8 steps for PCC mix design, I will have included some general values for pavement structures. PCC is obviously used in much more than just pavements. It's used in foundations, in building design, all these different applications. So if you go to the American Concrete Institute's ACI's 211.1-91, which goes over the mix design, they have to plan not only for pavements, but also for all of these other applications. So the first step is to determine the slump. And when you're looking at pavements, you're typically looking for 1 to 3 inches of slump for your typical mixture. And what does the slump influence? It influences the ease of mixing, placing, compaction, and finishing of that pavement surface. The next step, step 2, is to determine the maximum aggregate size. And the maximum aggregate size rules are pretty straightforward. An aggregate cannot be larger than 1/3 of the slab depth. So if you have, for example, a 1-inch aggregate, you need a minimum of a 3-inch slab of PCC. And also, you want 3/4 of a distance minimum clear space between reinforcing bars. So again, if you have a 1-inch size aggregate, that means you need 4 inches between the reinforcing bars. So there's 1 inch of aggregate and then 3 inches of the mix. Or of, that could be potentially aggregates or cement, but you don't want one aggregate taking up more than 1/4 of that space. After you've determined the maximum aggregate size, you determine the mixing water and air content selection. And this is also dependent on a variety of factors, including your aggregate size and your gradation. Aggregate size was chosen in step 2, but gradation could be chosen based on ease of local materials. Also the particle shape, the PCC temperature, whether or not you have entrained air, and of course chemical admixtures. So when we're talking about Portland cement concrete or PCC, you can also add something called chemical admixtures. And those admixtures can do all sorts of things. Pretty much if you have a set of concrete and you want it to do something different, chances are there's a chemical admixture out there that you can add to the PCC, which will enable you to do something different, something extra, something more advanced with that mixture. After you've determined your mixing water, you need to determine the water-cement ratio. And again, for pavements, it's typically 0.4 to 0.5. But you pick this water-cement ratio based on the strength and durability that you're looking for. So as you go through the ACI manual, you'll see tables recommending different water-cement ratios for different levels of strength and durability that you're looking for. Now, because you know how much water you're adding in step 3, and then your water-cement ratio, you can quickly find the cement content. And often there is a minimum cement content as well specified either by the agency or by the mix design that you're following. So if your water-cement ratio is low enough where the amount of cement is below the minimum, then you simply have to bump that up in order to account, in order to get the amount of cement that you need. Step 6 is the coarse aggregate content, and this is empirically based on mixture workability, and it depends on aggregate size. So again, you need to think about how workable your mix is. You go to the ACI manual, and you're able to determine your coarse aggregate content. And now when you think about what all is in PCC, you can figure out your fine aggregate content. Since this is a volumetric mix design, you usually do your calculation based on 1 cubic yard of mixture. So if you know how much water you have, how much cement you have, and how much coarse aggregate you have, you simply subtract those 3 values from 1, and you know how much fine aggregate you need for your mix design. And then finally, step 8, you need to do any adjustments for aggregate moisture. When you're doing a PCC mix design, you do not want to use dry aggregates because all of the water that you put in during the mix design, that's based on the water cement content. And if that water goes into the aggregates, then you're losing water, and your water cement ratio will change, and your mixture will not be as optimized as it could be. Therefore, the final step is to adjust for the aggregate moisture, and this is important when you think about stockpile management. So if you have a stockpile where it had either rained very recently or it's been dry for a long time, you need to constantly check what is that aggregate moisture level in the stockpile, and then you can do that final adjustment for your mix design. Those are the basics of the mix design process, the 8 steps, but then I'll talk a little bit about the mechanisms also behind Portland cement hydration in PCC. So how does a PCC pavement gain strength? You start with a liquid, and over time it sets, and then after a certain amount of time it's strong enough in order to take the loads that you need. But how does a PCC pavement gain strength? Well, on the right you'll see a little diagram with the cement particles in the water and aggregate paste. And as the cement hydrates, as it starts accepting the water, a gel forms at the surface of the cement, and the volume of your cement grain actually decreases. And as that gel forms and expands, you actually have a network, and that's in the second picture, that's called the initial set. And you begin to have a weak skeleton between the different cement particles. And over time, the initial set transitions into what we call a final set, and that skeleton will become very rigid and strong, and that's where you get the strength for your pavement layers. And then the specimens between the grains are filled with hydration products. So you can see the grains in that lower picture. Between connecting those grains are what are called hydration products, and that's what gives the structure and the strength to the Portland cement pavement. And here is a schematic of the time it takes in order to gain strength in PCC pavements. And there are 2 different sides. You have your air entrained on the left and your non-air entrained on the right. And air entrainment is a type of chemical admixture, and what that does is it changes how much air is in your mixture of PCC. And I won't go into those details, but you can just see here the differences when looking from 1 day to 3 day to 7 and 28 day, that strength gain over time as the concrete cures. And you can also see the difference in strength when you change that water cement ratio. So you have all these variables which are highly dependent on your local availability of materials that go into the pavement. It's also dependent on how you decide to design the pavement. And now going over to the AC mix design, this is divided into 4 steps, and we'll follow the Superpave mix design method. Now, I fully realize that the Marshall mix design method is used, especially with smaller agencies, counties and towns and such, and also if you're on the West Coast, you may use the Veeam mix design method. But for the purposes of this presentation, I'm going to focus on the Superpave mix design method, which is used for a lot of the interstates and a lot of the larger DOTs projects or larger city projects. The first step in the AC mix design is to select your asphalt binder and your aggregates. And this is based on your local availability, your environment, and your traffic. So what is the weather like in your area? What kind of aggregate sources do you have? What kind of asphalt cement sources do you have? And then what is the final product going to be on? Will it be on an interstate? Will it be on a small rural road? These are all the things that go into selecting the binder that you will use and then the aggregates that you will use as well. And once you have your materials, you then design your aggregate structure. And aggregate structure is very important for AC pavements because the aggregates actually lock together in those pavements, and the aggregates transfer the loads from the surface down into the base. So you need to take a lot of care when designing your aggregate gradation and your estimated asphalt content. And you do that through properties of the aggregate that you're using in order to get your asphalt content. And then your gradation is often determined by what application you're putting it on. If it's a larger gradation, those are sometimes on the lower levels of pavements, down there in the structure. If it's a finer gradation, that'll provide a quieter, smoother surface, so that's often put on the higher layers of pavements or the surface courses. But there are a lot of details that go into selecting your gradation and your estimated asphalt content. And three terms that you will need to be aware of during this process is your VTM, your voids in total mix, which is the same thing as air voids, your VMA, your voids in mineral aggregate, and your VFA, your voids filled with asphalt. So as you go through the process, you track these three quantities in order to make sure the mix that you're designing is matching those properties. So once you have your aggregates and your asphalt, and you have your estimated asphalt content, you compact multiple specimens at a range of asphalt contents. So you have your estimated asphalt content, and you often go plus 0.5%, minus 0.5%, maybe plus 1%, maybe minus 1%, and you can construct graphs, which we'll see in a couple of slides, to determine what is the voids that you want for the total mix, the mineral aggregate, and the voids filled with asphalt. And as you're doing this, you compact the specimens using the number of gyrations based on expected traffic. In the Superpave mix design, you use a Superpave gyratory compactor, and you have to design how many times do you want that to go around in a circle, and how many times it goes in a circle determines how much it will be compacted, and that is based on expected traffic. And finally, you figure out your bulk densities, your VTM, your VMA, and your VFA as you go along through there. And this is all taken from the Asphalt Institute Manual SP2. So a lot of these terms that I'm putting on the bottom of the screen, you can simply Google those and find more information about them online. The third step of your AC mix design is the selection of the design asphalt content. So you base that on the optimal VTM, which is generally 4%, sometimes it's 4.5%, and your allowable VMA and VFA. So if you go to your state agency, they've established limits on what VMA levels and what VFA levels you're able to use. And then you prepare specimens at that constructed voids with the optimal asphalt content. That is to verify that you are actually designing what you think you are at the optimal asphalt content. And then finally, they do have a moisture sensitivity test at the end of the Superpave design. And you test moisture condition samples, essentially samples that have sat in warm water, and dry specimens, and you test these in an indirect tensile strength test. And you can compute the tensile strength ratio, which is the conditioned samples, so the moisture conditioned samples, their strength, divided by the dry specimens, or the unconditioned samples. And there are usually state specifications for that as well. So I've been talking a lot about estimated asphalt contents and going plus or minus certain percentages of asphalt cement, and these graphs visualize that very nicely. On the left graph, you're designing for a certain air voids, and in this example it's 4%, so you compact samples at multiple different asphalt contents, and as you make that curve, you're able to determine what is the optimal asphalt content by taking a point from the 4%, going over to the curve, and then dropping down to the asphalt content. So you start at the 4%, you move to the right in your curve, and then you go down to determine your optimal asphalt content. And once you have that optimal asphalt content, you're able to input that for your VMA and your VFA, and then you go the other way. You go up and over to determine what the estimated VMA and what the estimated VFA are for these samples. Now, when you're estimating like this using 4 points, there may be a little bit of error into that. So that's why you go back and recompact samples at that optimal asphalt content. If you did not recompact those samples, then you would just be using data that you're assuming, you're interpolating. So you want to go back and make sure you recompact those samples. So in summary, for mixed design, for PCC, you do your mixed design based on the ease of mixing, your slab depth, and other strength needs. Then you simply go in order of the components. So you start with your water, and then I have a mistake here. You start with your water, then you go to your cement. The word air should not be in there. You start with your water, you go to your cement through the water-cement ratio, you determine your coarse aggregate, and you simply subtract those three values in order to find your fine aggregate. Strength gain generally takes 7 to 28 days. Again, this is highly dependent on application. If you're doing a surface street with low volume traffic, you may be able to open it up a little sooner if we're talking about road pavements. But if you're on an interstate, you may need to wait somewhere in between that 7 to 28 days in order to make sure you've reached the proper strength. And from a mechanism point of view, there is a chemical reaction of the cement with the water, and that's what gains the strength. Whereas with the asphalt concrete pavement, you are based on your aggregate structure and volumetrics. That's kind of your starting point for the mixed design. And you want to optimize your asphalt cement content. Asphalt cement is far more expensive than the aggregates that you're putting in there, so you want to make sure you're getting just enough in order to provide the mixture's needs, but you don't put too much in order to either waste money or cause possible future deteriorations, and also you don't want too less because that can also cause problems. At the end of the process, you do need to evaluate your moisture sensitivity. And then finally, instead of a chemical reaction with asphalt cement, you simply heat the asphalt cement, coat the aggregate, and then as it cools, it stays adhered to the aggregate, and it holds the aggregates together. So there's no chemical reaction in an AC pavement. Instead, you use heat. So now we know the components and how to mix them, but what happens in the field? I'll take a little break now. If you have any questions, please feel free to write them in the chat box. So the question from Andy is, will Superpave ever adopt a standard strength test like the Marshall method does? And I think this is one of the wonderful things about having an interactive future is Bob has said, not yet, they do not have a standard strength test. And I think Bob is from APAC, so it's good that I have some people in industry here, because as an academic, I start thinking about the research test. And there is research in different types of strength tests, but there is Superpave itself does not have a strength test at this point. And in fact, I'm not even sure if they're considering implementing one. You have to think about how all the agencies that use Superpave would need to buy the additional equipment, and is it worth the cost of that additional equipment, the additional training, the additional materials necessary in order to have that beneficial gain in the design. Is there anything else? Okay. Thank you for the question. We've talked a little bit about the basics of pavements, and now we're going on to and a little bit about the mixed design, and now we're going to talk briefly about the construction techniques of pavements. So when you're looking at PCC construction, you first need to start with the site preparation. You need to prepare the grade, which means you're building this pavement over some sort of native soil, or if it's a rebuild, you need to take into account what's underneath it. A very important step is establishing the string line. A string line determines the thicknesses of all the layers going down. So all the machinery is somehow attached or reading where that string line is. So as you go along and pave, you know the pavement is exactly the thickness you want at exactly the elevation you want, so that there are no mistakes down the road. And you also need to place your dowel baskets down. The dowel bars are used for load transfer between the slabs of concrete or any sort of reinforcing, but you want to make sure to get all that steel in place before you start the paving. And PCC construction generally uses a slip form paver. There has been some work done with roller compacted concrete, but again, that's one of those newer technologies that we won't be going over today. But in slip form paving, you need to deliver the Portland cement concrete, you need to place it, and on the picture on the right, you can see the spreading of the PCC behind the slip form paver. You need to set the header joints and the tie bars, so when you're going from either section to section, or when you're combining two lanes next to each other, all these different types of paving, you need to make sure that you're controlling the joints and the tie bars correctly. And then finally, once it's placed, you need to finish it. You may need to texture it. That goes back to providing enough surface friction. It needs to be cured, and during that curing process, you may need to insulate it. If the temperature drops too quickly, or if it's very dry out, you want to keep that moisture inside. You want to keep the heat inside so it's able to hydrate correctly and to gain strength. You can have the best materials in the world, the best mix design in the world, and the best construction in the world, but if it doesn't cure correctly, your pavement will not perform as it should. And finally, after the pavement has been placed and is cured, you need to joint it. Often you go in there with a saw in order to saw a joint in there that will force the crack and joint to occur at that location. You need to clean that out and then to seal it immediately. If you do not seal it, materials can get inside that crack, water can get inside that crack, and over time that crack will get larger and it will deteriorate. And I point you to the National Concrete Pavement Technology Center Concrete Pavement Construction Basics, which is a nice document available online that goes through all these steps in more detail. Asphalt concrete, or AC, new construction. Note how I put new construction under here. This is assuming that you're building a brand new road. Things change if you're rehabilitating a road, if you're doing maintenance on a road, or if you're putting an overlay on an existing road. But assuming that it's new construction, you need to prepare your site, which includes preparing the grade and establishing your elevation, just like the PCC pavements, and then you place your base down. In the picture on the bottom, you can see the paving train, and that is riding on top of an aggregate base that had already been put down. And the aggregate base needs to be a certain thickness. They usually compact it a little bit, and they smooth it out so you have a nice smooth surface to lay your asphalt concrete on top of. And when you do go to the paving, you first need to deliver it. Often asphalt concrete is remixed now. In that picture on the bottom, the machinery in the middle, the RoadTech machine, that's a material transfer device, and what happens is the material goes from the truck into that material transfer device and it mixes. And that mixing eliminates a lot of the segregation, both rocks and temperature, so you have a very homogeneous mixture going into the paver, which then lays it down. After the pavement's been laid down, there's often either pneumatic and or steel wheel rollers that go over that pavement structure and that compacts it downward to your design asphalt or design air voids content. You need to think about your joints and your edges. If you're paving two lanes, you need to tie those together. Make sure that there's a nice smooth surface in between them, so if cars are passing, there's no problems with that joint. And then on the edge, often you tie it together with either a shoulder or some sort of granular shoulder, and you want to make sure that those are all level so that if someone does happen to drive off the side, there's no problems associated with that. And as you're building these layers of asphalt concrete, recall that they're each about 2 to 4 inches thick. You may need to put several layers down. Often you'll have these tack and prime coats in order to adhere those layers together. And I wanted to point out here that there have been some studies where they saw a joint into the asphalt concrete pavement. And what that would do is it would force a crack to grow there, which in theory makes it easier to maintain, because if you put that crack in and immediately point the sealant in, then that crack will form at that location. But if it's already sealed, the material and the water won't get inside that crack. But asphalt concrete cracks very uniformly due to either thermal cracking or other types of cracking, and that usually provides enough stress release. You need to get out there and seal those cracks in an efficient manner, but there have been talks of using joints like the PCC pavements. Now, looking at some pavement distresses, the Federal Highway Administration has a very nice distress identification manual, also available online for free download, that goes over these. And there are many different distresses and many different subsets of each distress. Both PCC and AC are susceptible to cracking, but the mechanisms behind that cracking is very different. The cracking in PCC often is either corner, durability, longitudinal, or transverse, and that's generally where the pavement, the loads are exceeded, so it literally snaps at some point, whether it snaps in the middle on the longitudinal, or if a very heavy load is placed on the corner, that corner could block off, and once you have a crack in PCC pavement, it's very difficult to maintain. With asphalt concrete, however, with ACC, you often have fatigue cracking, which is multiple wheel loads will start cracking at the bottom of the pavement, and that crack can move up. You also have these different types: block, edge, longitudinal, and reflection. However, the mechanisms behind these cracks are a little bit different. But the important part in either pavement is once a crack occurs, it does need to be properly maintained, so no material gets in there, no water gets in there, which makes the crack larger and deteriorates the pavement more quickly. Other distresses in PCC include joint deficiencies. You could have seal damage. When you seal a joint, if that sealant comes out or if it gets damaged by traffic, that can be a problem. Also spalling, that's where it literally just kind of flakes up right at the joint. Surface defects and other miscellaneous problems can occur with PCC. Whereas with asphalt concrete, you have patching and potholes. Surface deformation, usually in the form of rutting, sometimes at heavy intersections, shoving. You can have many surface defects. Bleeding comes from having too much asphalt in the mixture, raveling from not enough, and then also some other miscellaneous distresses. And I went over these very, very quickly, but if you'd want to look more into any of the details, I encourage you to look at the Distress Identification Manual. So what kind of maintenance is available? Again, lots of information on this slide, lots of details associated with each one. We're just kind of looking at a global view of PCC maintenance. When I think of maintenance, I think of several different areas. There are preservation types of maintenance where you're just kind of maintaining the existing pavement. Nothing is fundamentally wrong. You just want to make sure it doesn't start deteriorating too quickly or something fundamentally does happen. For example, a functional maintenance is a partial depth repair. If something's wrong with the top 2 or 3 inches of that Portland cement concrete pavement surface, you may need to actually take the whole thing out and replace it with new PCC. Or, like the picture on the right, if you're losing a lot of surface friction or if you have faulting, you may need to do some diamond grinding in order to get that surface friction back, or just to take a little bit layer off the top. Also, a lot of places go with a thin AC overlay that provides not a whole lot of structural capacity, but it does allow for a smooth, quiet driving surface. Then if there are fundamental problems, you may have to do some structural maintenance. For example, a retrofit load transfer. If you're having problems in between slabs, you might need to go in and either take out the old dowel bars and put in new dowel bars, or if the pavement was designed without dowel bars, you may need to put those dowel bars in. Also cross-stitching, slab undersealing, even removing and replacing. These are all examples of structural maintenance. And I'd like to point you to the Texas Transportation Institute's Guidelines for Routine Maintenance of Concrete Pavement. These go over all these different steps in detail, not only what causes them, but also what can prevent them, and then how to fix them if they occur. AC maintenance is a little different. You'll see a lot of talk about surface treatments, and that is because AC surfaces age very quickly over time because of the sun, because of the wind, because of the elements. You need to rejuvenate that upper surface layer so that it doesn't get old and start cracking and deteriorating. So there's various ways to do that, everything from fog seals, chip seals, slurry seals, and to crack filling. So those type of things don't add any sort of structure. They don't increase the carrying capacity of the road, but they do rejuvenate the surface and continue providing a smooth, safe pavement layer for the traveling public. Overlays, if you need to add a little bit of structural capacity, or if the distress is so bad on the surface, you might consider an ultra-thin bonded overlay. A standard overlay does something very similar, but it adds a little structural capacity. And then finally, if you're having severe structural problems, you could consider cold-in-place recycling. And that mills up the top 2 to 3 inches of pavement, mixes it with emulsion, and that can actually increase the structural capacity of that road. And full-depth reclamation goes down into the base layers below the bituminous material and mixes that, also increasing the structural capacity. So both PCC and AC both have the preventative maintenance, whether it be surface treatments or crack sealing, but then also it kind of transitions into, if there's fundamental structural problems, what kind of maintenance can you do in order to get more life out of that pavement surface. So in summary, all pavements must serve their purpose. They must be smooth, and they must provide a safe driving surface, especially for roadways. There are similarities and differences in both the materials and designs from PCC and AC pavements, and also field construction and maintenance is critical to pavement's long-term success. What I went over today is a very broad overview of these 4 different categories. Some of the information I got from a website called pavementinteractive.org. This is kind of like a Wikipedia of pavements. Very interesting, very good material on there, so if you want to explore that, I can encourage that. But at this point, the technical presentation is over, and I will open the floor to questions. As people are typing their questions, just as a little wrap-up, I have all of your email addresses, so I will email you a Professional Development Hour completion certificate. You simply need to write your name in, and then you'll receive 1 professional development hour. You can also re-watch and re-listen to these Pavinars through the website, and I'll also post this PDF or the presentation in a PDF form on the website, so you can go back, look at some of the information that was given, go through some material that you know, I may have gone through a little too quickly, you want to dig a little deeper into. And I encourage you, if you have a topic that you're interested in, please submit it via the website. That's how I'm going to get the topics for next spring. I have my 4 presentations set for this fall, but next spring I'm looking for topics. And these Pavinars are meant to help you in the pavement community do a better job of understanding what you're working with or increase some knowledge in an area. So really, I want this to benefit you out there in the pavement community as much as possible. I also want to remind you the next Pavinar will be Tuesday, September 6th. All Pavinars will be the first Tuesday of the month at noon, and it will cover basic asphalt concrete maintenance principles. So what I covered in 1 slide in this presentation will be an entire Pavinar for the next presentation. So I thank you all for attending, and I open the floor to questions and discussion. Thank you very much. So we had a question on slide 23. In this slide, you have your truck delivering the mix. Then you have your material transfer vehicle, or MTV, right here remixing, and it goes into the hopper. And I have not heard of an MTV having heating capabilities. Now that doesn't mean it's not true. I encourage other people to hop in if they may know whether or not for sure. I have not heard of it, but if they don't do it, it probably wouldn't be a bad idea. I think one of the reasons that you may have a problem with a heated MTV is that if the mixture gets too cold, then it may actually start kind of hardening inside the truck, and reheating would start deteriorating the product. So as you see also in the chat boxes, the other participants haven't heard of it, but it's an interesting idea, and as someone in research, that's certainly something that could possibly be looked into. Are there any other questions? Well, again, thank you very much for participating. This is actually I've been calling it the Fall 2011 Pavinar series, but this is actually the first Pavinar. So I'm very excited that we had some good participation, some good questions, some good discussions, and I purposely did not advertise this first one because I just wanted to make sure that the electronic end of things, the software end of things was working properly, and I had a couple people here at the University of Arkansas also watching and helping me with that. But I highly encourage you to contact your friends and colleagues and try and build some momentum, and I'll also do a little more advertising in the future. But thank you for joining today. If you have any follow-up questions, feel free to email me. Please submit topics for future Pavinars, and thank you very much. Have a nice afternoon.